Hello everybody, and welcome back to Microchip's Design Week 2021. I'll be your host today, Clifford Swartz, and today is day 4 of Design Week. For those of you that may not know, Design Week is a 6-day virtual event where you get the opportunity to watch live demos, speak to real-life Microchip experts, and furthermore, actually attend classes that those experts designed specifically for you in this event. Today's topic is eMobility and ADAS, and I have quite a group with me to discuss it all with you. But before we do, I'm going to throw it over to Wayne Freeman in the booth, and he's going to tell you how to participate. Hello, Wayne.
Hey, Clifford, how's it going?
It's going well. I like your shirt, Wayne.
Oh, I like your shirt as well, Clifford.
Thanks.
Hey, everybody on the stage. It's a wonderful, wonderful Tuesday. We're happy to have you with us, broadcasting live on YouTube, Facebook, and LinkedIn. So just wanted to kind of give you a little bit of ground rules, set the stage here. Please make sure you like, share, and subscribe to all of these channels. Please like the video if you haven't taken an opportunity to do that already. Now, this is going to be an awesome panel discussion, and I'm going to be participating in the chat with you guys. I'm kind of going to be the conduit or the link between the chat and the panel discussion here. So any question you ask, we'll try to get an answer for either in the chat, or I'll actually choose selected questions and ask them of the panelists. So it's going to be really cool. Now, let's talk about Design Week. This is a week that was so action-packed that we had to do it over a 2-week period, which is very cool. Today's the 4th day of our Design Week event. Now, as always, the live streams are just the beginning. We continue the party on our event portal. And if you don't know what that is, go to microchip.com/designweek, of course, in another tab. And if you haven't registered already, please register. If you have, then go ahead and click in, and you will be able to basically see all the other cool stuff that we have planned for you for Design Week. So directly after this live stream, there will be talk tracks and demo sessions and all sorts of really cool things that you can view and interact with. You can also set up a one-on-one meeting with. Actually, I think some of the guys on the panel are going to be available to discuss their performance today, the discussion today. If you go to the eMobility and ADAS section, so you'll also be able to see. Let's see what else we have. We demos, which are very cool. I'm checking my screen over here where Clifford is rolling through here.
Yep.
So there's a demo button, meeting button. There's a chat function down below if you would like to actually chat with any of the attendees, or you can have a chat. You can start a chat with some of the folks who are Microchip employees if you have questions. In addition to that, let's talk about the trivia function. Trivia is pretty cool. So we basically asked our experts to kind of seed some questions and polls and whatnot for for Design Week, just to kind of make it fun and interactive. If you get the questions, if you answer the questions correctly, you may be selected to win a prize, which can either be a 99.5% discount on a dev board or a gift card. So lots of cool stuff. Now, if you missed any of the first 3 days, you can also find links to the content in this portal. So if you missed that, go back after today's over, like maybe later on tonight, with a good cup of coffee or a good cup of tea or whatever, and watch the other content that you may not have seen. So I'm gonna not speak so long today because I'm really excited to get this panel discussion underway. Clifford, I'm going to toss it back to you. You guys have a great time.
Thank you very much, boss. So, like I mentioned, we have quite a few guests. We have a full house in the studio, and we also have some guests online. Starting to my left, we have Dave. How are you?
Just fine, Clifford.
I'm happy to have you here. To Dave's left, we have VJ. How you doing?
Hi, Clifford. Good to see you again.
Good to see you again. Sort of based off that, VJ and Dave has been on, I think, like 3 or so different live streams in the past. And if you're familiar with our other live streams, you'll also recognize Orlando. How you doing, Orlando?
Doing well, thanks.
Good to have you here. In addition to these 3 gentlemen, we also have 2 gentlemen, and you can see them now on the screen. We have Mike and Stefan. How you guys doing?
Hey, great. Good, thank you. Clifford, I also like your shirt.
Thank you very much, and I like your whole suit jacket. It's very impressive. It's good. So these gentlemen are here to talk to us about eMobility and ADAS. We're going to break it out into two different sections, the first one being eMobility. Dave, my first question is for you. Do you mind breaking down for the audience what eMobility means?
Sure, Clifford. So eMobility or electromobility has to do with vehicles that use electric motors for propulsion. So this includes your full electric vehicles, also known as battery electric vehicles, such as Tesla's, NIO, Nissan Leaf, Mustang Mach-E, and many others.
Right.
So it also includes your hybrid electric vehicles. So these are vehicles with an internal combustion engine and an electric motor. And these are like the Toyota Prius, Ford Fusion, Honda Insight, and there's many others as well. It also includes plug-in hybrid electric vehicles. So these are hybrid electric vehicles that also have the additional capability where you can plug in to an external source to charge the batteries. So plug into a wall charger or a charging station. It also includes what we call mild hybrid electric vehicles. So these are vehicles with an internal combustion engine and a small electric motor that's powered by a supplemental 48-volt battery.
Gotcha.
So the motor itself, it's used for start-stop function, and it can provide a little bit of power assist to the internal combustion engine in certain situations, but it's not powerful enough to provide vehicle propulsion by itself. And there's other things such as e-bikes, e-scooters, micro-hybrids, but those are the main ones. So as you can see, there's just a lot of vehicles that fall under the e-mobility umbrella. And you know, all major automakers either have or are working on new electric vehicles or electrified versions of current models. And there's a lot of new players coming on board too. So Rivian, Lucid, Byton, Faraday Future, and many others in China and all over the globe.
Thank you very much. So my next question is for Stefan. Stefan, do you mind giving us a breakdown on what some of the key areas within eMobility Microchip is specifically addressing?
Sure, Clifford. So the E in eMobility stands for electric, as mentioned by David already, but the E in eMobility can also stand for efficiency, because everything is towards the goal to reduce CO2 emission. That's why everything is going for electric, and to extend the range of the electric car. So we have prepared one slide which shows Microchip in electro vehicles. So you can see several different applications where we are positioned in the electric car. And while several of these areas are changing and evolving from the traditional combustion engine to electric engines, as an example, for sure there's less need for an engine cooling fan in an electric car, which had the need for reducing audible noise during a start-stop engine condition. But there is definitely the need for a battery cooling system with a higher efficiency. So definitely a pretty big need for motor control, as electric cars need more auxiliary pumps, fans, compressors. And beside this, the more obvious area, of course, is towards power conversion, power control. So you can see onboard AC charging, power factor correction, DC-DC converter, the conversion between the board net voltages from 12 volt, 48 volt, bus balancing, battery management systems, and all of them need high power integrated devices. So as an example, if we look onto an onboard charger, I have prepared one slide which outlines a couple of those building blocks. So one is, of course, the microcontroller, which is integrating the whole digital signal. But we also talk about the whole analog chain around that, operational amplifiers, temperature sensors, communication, whether this is Ethernet, LIN, or CAN-FD communication, but also rounded up with the higher voltages, MOSFETs, and diodes using silicon carbide technology.
Thank you very much for that breakdown. My next question, Vijay, I see that at the heart of this block diagram is the DSPIC33. Why is that such a perfect device for eMobility solutions?
Yeah, that's a good segue into the next topic. So yeah, like we talked about, so we're seeing a trend in electrification of vehicles. In addition to standard vehicles, we also see things like e-bikes and e-scooters becoming important, in addition to agricultural vehicles as well. So there are several challenges in managing power in these applications because of the generation and the distribution and control of high power. That's the key point here. The high power needs to be controlled properly. And the message here is that we support a broad range of eMobility solutions for power conversion as well as motor control and functional safety requirements.
Gotcha. And so I see your last point being power conversion, motor control. I kind of want to dive deeper into those. Is that okay?
Absolutely, yes. For power conversion, there are typically in any electric vehicle there are multiple power conversion stages. We saw the example that Stefan provided for the onboard charger, and then in addition to that, there is DC to AC inverters as well that convert the DC voltage from the battery to AC to drive the AC motors in the vehicle. And the drivability of the vehicle is very much dependent on the performance of the inverter. So that's a really key point here in an electric vehicle. And also there are multiple DC to DC power conversion stages here. For example, the battery voltage is typically in the range of 200 to 800 volts.
Wow.
And that needs to be stepped down for powering in-cabin applications like the doors and the windows and steering wheels and other things like that. That's typically in the range of 12 to 24 volts. So you need to step that battery voltage down to support these voltages. And the key point here is that efficiency is key. And you need to be able to provide high efficiency power conversion. And the DSP controller and the software algorithms provide high efficiency power conversion for power conversion and as well as for battery charging applications as well.
Gotcha.
So we have things like the PFC design. So Microchip has algorithms that we provide for sophisticated PFC implementation. And also we provide the flexibility to customers who would like to optimize the PFC performance for their final implementation. And typically with digital control with the DSP, you can operate at higher frequencies, and you can implement things like interleaved PFCs, which help minimize component size and component and overall board space and things like that. So
I got you. So there's a lot of power conversion, and it's incredibly important to maintain the efficiency with that.
Absolutely.
I have to imagine there's a lot of motor control as well. Do you mind breaking that down?
For sure, yes. So, and in any vehicle, and even specifically electric vehicle, the electric motors are typically augmenting mechanically powered propulsion systems, and several applications like automatic doors and windows, like sunroofs, even your seats, your power seats, all are requiring motors.
Right.
And I mean, you want to have high efficiency motors, and the DSP provides the right algorithms for providing or implementing high efficiency motor control. So typically, the DSP is designed for DSP operations and real-time control. So this combination helps provide a tight control loop required for high efficient power or motor control here.
I got you.
So in this case, in addition to the DSP core, there are several peripherals like the ADCs, the high-speed ADCs, high-resolution PWMs, and the op-amps and comparators. All of these work together seamlessly, independent of the CPU, to optimize control loop execution time. And this frees up CPU bandwidth to run algorithms like the field-oriented control for optimizing motor efficiency.
Gotcha.
And in addition, because of the fact that there is CPU bandwidth remaining, we can run algorithms to implement functional safety in functional safety applications.
Which is becoming more and more critical in automotive and in every space, quite frankly.
That's right, yeah.
Cool. Thank you very much, Vijay. Orlando, my next question is for you. Vijay was mentioning ranges in the hundreds of volts, and so with that being the case, how is Microchip able to address the needs of all these different hardware designers?
Yeah, thanks, Clifford. We can. This is a new capability for Microchip. Just over 3 years ago, we acquired Microsemi. Microsemi served this space for many years. Prior to Microsemi, this group was Advanced Power Technologies, or APT, and they go back 30 plus years in providing solutions within high power devices. So a lot of expertise, a lot of capabilities that came to Microchip with that acquisition. So very excited to have that. When you look at the electric vehicle, the high voltage battery is either 400 volts or 800 volts. So as far as power devices that serve those systems, For 400 volt batteries, you typically have power devices that are rated between 650 and 750 volts. And for the 800 volt systems, you have power devices rated at 1200 volts.
Wow.
So yeah, very, very high voltage. And at Microchip, we support silicon carbide power solutions today. For the 400 volt systems, we have 700 volt power discretes, which are both the die and the package discrete options. We also have power modules to serve these areas. So again, for 400 volt systems, we have 700 volt solutions, and for 800 volt systems, we have 1200 volt solutions. In addition to that, these systems require the drive, the gate drive. Vijay talked about the control. There's the control, the drive, and the power stage. So for the drive, we have a growing family of intelligent gate drive solutions. And when we say intelligent, we give the designers the ability to configure the turn on and the turn off of those MOSFETs. And this helps to maximize the efficiency and minimize the overshoot and EMI within those systems, which is extremely important, especially within an electric vehicle.
Got you. And so all of this was coming back to silicon carbide. Do you mind talking about what sort of applications you think are considering transitioning over to silicon carbide?
Yeah, new exciting technology, silicon carbide, you could see from the graph here, there's rapid growth in this area. And although automotive is one of the main driving forces, one of the main driving markets within the silicon carbide technology, a lot of other areas are benefiting as well. So when you look at applications, a lot of silicon-based designs are limited with continuing to lower the cost of those systems and continuing to innovate those systems, so making them smaller and lighter. Silicon carbide helps to overcome some of those challenges. The characteristics of silicon carbide help offer lower on resistance, offer higher junction temperature, help with faster switching. So really this results in the system being more efficient, being lighter, and being smaller. So we talk a lot about silicon carbide in automotive, but there's a lot of other applications within medical, industrial, renewable energy, and even aerospace and defense that are taking advantage of this new technology. And it's really exciting. I mean, it's a change happening, a significant change happening, and it's presenting a lot of opportunity, not just to Microchip, but to our clients to expand into new spaces, new applications where maybe they didn't play before.
Right. Thank you very much for the breakdown. To dive a little bit deeper into actual e-mobility, where do you see silicon carbide benefiting the electric vehicle market the most?
Yeah, automotive, as I mentioned, is one of the dominant drivers for silicon carbide. You have to look at it both externally and internally, or what we call on board. And it's not just in passenger vehicles. When we talk automotive a lot, you think of passenger vehicles, but it's beyond that. You have commercial vehicles, you have agricultural equipment that Vijay mentioned. You even have other transportation like trams, trolleys, and trains. All of these benefit from this new technology, and they're going to electrification. When you talk about charging infrastructure, how are you going to charge all of these new electric vehicles that are going to be on the road in a realistic and practical time? So, silicon carbide, when you look at charging infrastructure or charging stations, it not only helps with minimizing the charge time, but it helps for those charging stations improve the efficiency and make them smaller. When you look on board the vehicle, onboard charging. So onboard charging, or OBC, manages the charging of the high voltage battery.
Right.
You want to make those systems, very light, so improve the range of the vehicle. You want to make them small, so it gives more flexibility within the architecture of the vehicle. So silicon carbide helps to solve some of those challenges. And then similarly, you have DC to DC and DC to AC converters. So an example of a DC to DC converter is you would take the 400 or 800 volt battery, you would convert that down to an auxiliary voltage such as 12 volts, which is used by all of the other electronic control units in the vehicle. For a DC to AC, you would convert that to an AC output. So maybe where you can use an external plug.
Right.
And then one of the main applications on the electric vehicle is the motor drive. And that is, there's a lot of vehicles there's some vehicles on the road today that use silicon carbide. And this silicon carbide is used in what we call the traction inverter. And basically that takes the high voltage battery, converts that to a current source to directly drive the electric motor. And that's quite an exciting application, especially for us in wide bandgap and silicon carbide, because there's a lot of content in that. It really helps to improve the range of the car, and it's really helping to the growth of this technology within electric vehicles. So very exciting time. Me being in silicon carbide and wide bandgap, it's quite exciting. So,
absolutely.
Yeah.
Thank you very much. So we're going to shift gears. You like that one? Now, and we're going to talk about ADAS. My first question, once again, over to Dave. Do you mind breaking down what ADAS stands for and why people should be interested in it?
Sure. So ADAS stands for Advanced Driver Assistance Systems. And these are systems that help the driver control the vehicle either by alerting the driver of certain situations or certain conditions, or by actually taking control of some portion of the vehicle, either taking control of the steering, acceleration, deceleration, braking, things like that. On the slide here, you can see several examples of ADAS systems at the top. And then at the bottom are areas where Microchip plays in these systems. So we have solutions for sensor processing, communications, for the central compute module, the vehicle computer ADAS controller, however you want to call it. But as I mentioned, there's a lot of examples there at the top. So you can see things like adaptive cruise control, which are systems that will actually control the acceleration or deceleration of the vehicle. And you have lane departure warning or lane departure assist. So departure warning, alerts the driver, whereas the lane keep assist will actually steer the vehicle and keep it in the lane. So different functions, but a lot of different areas where ADAS plays. And one thing to note is with regard to the term ADAS, a lot of people conflate ADAS with autonomous driving, as we will do here today as well.
Right.
And there's a lot of similarities, there's a lot of overlap. There are some differences. ADAS, as the name implies, are systems that assist a driver. So you find these in what we refer to as level 1, level 2 autonomous vehicles, where the human driver is still in control and has these systems to help them with the control of the vehicle. For autonomous driving, which is level 3 and above autonomous vehicles, the vehicle is actually the one doing the control. And so these systems, they do more than just assist, they actually control the vehicle. But as I mentioned, people will use ADAS to refer to all levels of autonomy, and they just basically paint with a broad brush.
Right. Thank you very much for the background. My next question is for Mike. Hey, Mike. Autonomous vehicles are increasingly being labeled as data centers on wheels. Why is that, and what implications does that have for Microchip as a whole?
Okay, yeah, so autonomous driving really needs a fundamental change in the in-vehicle networking. Moving from traditionally today, we have a distributed domain-based architecture where the ECUs are application or domain specific. ECUs mean the electronic control units. And we're moving towards what we call a centralized compute platform with zonal ECUs. And the difference with zonal ECUs, as you can see there, they're responsible for collecting all the data in that zone, irrespective of what the application, what the domain is. The actuators, the sensors, neighboring data from ECUs for redundancy. And then they move all that data up into that central compute platform. Just like a data center, that contains a number of high performance SoCs, processors, to process that data for the behavior of the vehicle. And for this, the connectivity, Ethernet very much is the enabler for autonomous vehicles. It's standards based, backwards compatible with the speeds, it's secure, connects from device all the way to the cloud, and it also reduces costs. One of the advantages is that you remove gateways. If you have, like we have today, multiple buses, technologies in the vehicle, you have to have these gateways to translate, if you like, one technology to another. That's costly, and it's also quite complex. So it saves costs there. It also saves costs on wiring, both the weight and the amount of wiring you need. On the question for Microchip, that's exactly what we do. We do connectivity around the compute platform. So we offer not just the automotive Ethernet solutions, we offer all those buses and technologies within the vehicle.
Thank you very much. And so correct me if I'm wrong, but the compute platform that you were mentioning, that functionally serves as a data center, right?
Yeah, absolutely. You've got it. So I think we've got a simple example just to show that. Very simple. We have 4 zonal ECUs. Each one has a high definition camera, consuming just over 10 gig or more. And then 1 or 2 other sensors like LiDAR or radar. And so those zonal ECUs will collect that data and the neighboring data for redundancy and push that up to the central compute. And here you can see how really bandwidth explodes very quickly, accumulates. So we have 25 gig per zonal ECU, 50 gig with the autonomous, with the redundancy. And then you can see we've got up to 200 gigs worth of data that has to be processed within that central compute platform. And that compute platform is really a bank of multiple high-performance SoCs, maybe 2, 3, 4, 6, or even more, very much like a data center. And one of the things when you look at those SoCs, same technology as the data center, for their de facto preferred high bandwidth interface, that is not Ethernet, that is PCIe, commonly used. So here we would advocate you need a high performance PCIe switch in the compute platform to move that data around those SoCs within the compute platform.
Gotcha, thank you very much. And just to keep it simple, that's PCIe for the inside and Ethernet for the outside, right?
Yep, that's an excellent summary, really. So yeah, you have PCIe on board, moving data across the SoCs, and then off board, i.e. cables, you have an Ethernet in-vehicle network.
Cool.
That's right.
Thank you very much. And so do you think the future is going to move towards Ethernet as a whole, purely just Ethernet, or what do you think about the future of in-vehicle networks?
Yeah, I guess that's the vision. We often talk about the all Ethernet vehicle. It's the vision, maybe it's a dream. I think the reality, certainly a dream for me. I do Ethernet, so yeah, it's probably my dream. Others as well. But the reality is that we know there's a lot of well-established, very good bus technologies in the vehicle today. We all know about CAN and LIN, very low cost, very good at what they're doing. So I don't think in the near term, at least, they're going to go away. So you are going to have a mixture of technologies and buses in the car. But I think the one thing I can say, and it's for certain, is that going forward with autonomous vehicles, with electric vehicles, Ethernet is going to dominate, and there's going to be fewer and fewer of those buses within the vehicle.
Gotcha. Thank you very much. My next question is going to be directed over to Dave. Dave, there's been an increasing focus on autonomous vehicles and their ability to accurately determine objects, foreign or not, in the road. Do you mind talking a little bit to the audience about your thoughts on some of the best sensing technologies?
Yeah, sure. There has been a lot of debate, discussion,
right.
Publicity about sensing. and a lot of development going on. Sensing is a very key part of ADAS, because for a vehicle to be able to self-drive, it needs to be completely aware of its surroundings. And there's a lot of different technologies that are in use today and are being developed. Some of the things like cameras, of course, radar, ultrasonic, and LiDAR. And LiDAR is one that's getting a lot of attention now, and there's a lot of development going on. And we have solutions here at Microchip that can help designers develop a LiDAR module. And there's different ways of doing LiDAR. There's solid state LiDAR, there's MEMS-based LiDARs, there's hybrid versions of that. So there's a lot of different ways. But here's one example of ways to do solid state LiDAR. So we have everything from the computing portion with the FPGA. We have all the surrounding analogs, so the voltage regulators, temp sensors, communication devices, timing devices, security, and all that. So we really can offer a complete solution, a total system solution for a LiDAR module, LiDAR control module. But as far as what's the best sensing technology, a lot of that depends on the use case and which criteria are the most important. There's trade-offs between range, field of view, accuracy, resolution, and of course cost and size are also important criteria when you're talking about sensing. And then the use case also will help determine what's the best technology. So as you move up into higher levels of autonomy, you need more range on your sensor, as opposed to a lower level of autonomy where the human driver is in control. You don't maybe necessarily need the long-range LiDAR or the long-range radar, and you can get away with lower-cost cameras and things like that. And the use case is also an important consideration. So when you're talking about vehicles such as robo-taxis or long-haul delivery trucks that are theoretically on the road 24/7, the higher cost sensors, the long range LiDAR and things like that, those costs can be absorbed a little better because you're amortizing over many more miles, as opposed to a private vehicle that's sitting in your garage or in a parking space, 95% of the time or more. And then there's also things like, if you're talking about taxis or delivery trucks, those higher cost sensors are offset by the savings you have by not having to hire and pay a driver, of course, for the vehicle. So again, the best technology depends on what you need, what specs or requirements you have to meet, or what use case there is for the vehicle.
Got you. Thank you very much. Stefan, my next question is for you. Autonomous vehicles are changing the way that drivers actually interact with their cars. Talk to me about what you think the future of human-machine interfaces in these vehicles is going to look like.
Okay, thanks, Clifford. Good question. Well, when we look into short to mid-term towards semi-automated devices and vehicles into high levels of autonomy, we can pick an example from one of the previous slides listing some ADAS applications. As we can see the steering wheel. As of today, this was evolving already a lot from only steering function to also ADAS support functions, measuring hands-on, hands-off detection to see if the driver has his hands on the wheel or if he can take it off. Driver position sensing is done, everything is touch-based. You see more and more pads, sliders, even displays on a steering wheel are coming in. And medical functions are getting more and more integrated. Definitely ADAS is coming into areas where there was no safety function previously. A good example is also the audio acoustic noise generation, which is there to, turning from a non-safety needed system to a safety critical element, because now it's needed to generate noise at a certain low speed from an electric car to just warn people around that there is a vehicle coming. So systems which are informing other people around in the environment of an autonomous car is what is going to do next, is getting more and more important. This will be done visually with, for instance, exterior lighting effects, projections on the street, as an example. but also interior dynamic light effects, taking over the ambient light color in the car with fancy dynamic light effects. When the driving situation is changing from an autonomous driving mode to maybe a situation where the driver still needs to take back control quickly or within a certain time, new technologies are needed, and something we will discuss in one of the sessions later on about dynamic interior light effects is one of the hot topics.
Cool. Thank you very much. And one last question for you, Dave. Where can people go if they wanted to read more right now on the web?
Well, there's two places I would direct people. So if you're interested in ADAS, go to microchip.com/ADAS, and you'll see different solutions for different ADAS applications and more information there. You can find information on our products.
Gotcha.
As you scroll down, all that. And the other place, microchip.com/eMobility. So same thing. You'll find our solutions for different eMobility applications and again, products and tools and things like that.
Cool. Thank you very much. That brings us to the end of the presentation portion, but we're not done yet. Wayne, I am sure we have a lot of questions. Hit me with your favorite one first.
Let's see. Well, we have quite a few, and I've actually been spending a lot of time in the chat, so thank you all for keeping me super busy out there. Let's see. I'll start with a question from Jorge. How do you deal with redundancy for critical systems? And I think this is probably going to be a good one for either Dave or Stefan. So correct me if I'm wrong, guys.
Yeah, I can take this question. Well, it's a great question because we integrate more and more into autonomous core independent peripherals. So our peripherals getting more intelligence, therefore they are getting more and more redundant. A good example is also logic elements we put into our microcontrollers, into our DSPICs, into our PICs, into our AVRs, and SAM products. So per se, this is already driving a lot of functional safety and redundancy. But this doesn't end. We also have dual core devices. The DSPIC33CH family is one of the examples. Is a device which is definitely targeting safety critical elements. And yeah, with the dual core, you can design redundancy and also according to functional safety standards like ISO 26262.
Awesome.
Good question.
And I guess that actually dovetails in with another question that was asking about whether or not we would use single core or dual core for these types of applications. So you've kind of gotten two birds with one stone. Next question, let's see, from Sugania. This is she's a machine learning engineer, and she wants to kind of get an understanding of the application of computer vision in ADAS. Now, this kind of crosses two different areas. So, if this isn't in your direct area of expertise, guys, we did actually do last Thursday, a machine learning live stream, and we actually have machine learning experts. But I just kind of wanted to throw it out there to see if there was any thoughts from you guys.
Well, as far as the application of computer vision, as I mentioned, one of the key requirements in ADAS is for the vehicle to be able to be completely aware of its surroundings. So
right.
you need different vision systems and different sensing systems for the vehicle to be able to know if there are objects in the road, what the weather is like, what the surrounding environment is like, and then even for we normally think of ADAS sometimes driving at the higher speeds and all that, but even getting around in parking lots and things like that to have the vision of what's next to you and what's around you, and so it's a critical piece. So if I understand the question, right, the concept of computer vision, if we're talking about why is that important for ADAS? I mean, it's almost like you just can't have these systems wouldn't function without having these vision systems available, or these sensing systems available.
Awesome.
Cool.
And Dave, I just wanted to comment that I think we also have a lot of new devices which you would not traditionally link with Microchip. One of the examples is, if we stay with image processing, vision systems, an FPGA. We have automotive rated FPGAs now with the acquisition of Microsemi. And there is a family which is the PolarFire and newly the upcoming automotive PolarFire SoC device, which is also serving much, much more performance, where we can bring in a lot of values and benefits with such kind of solutions, I think, in exactly such kind of applications.
Absolutely, and we have a talk track, I believe, in 1 hour and 20 minutes that discusses that exact thing, so tune in for that if you're interested.
Yes, absolutely. And I will say we actually had Diptesh Nandi on last Thursday live, and he actually did talk about basically the use of the PolarFire FPGA family and computer vision. He had a really cool demo that we shared. So please take a look at that. Just go back a few days on the YouTube channel there. Let's see. So there were a few questions around the protocols that are used for eMobility, and Mike, I know you touched you touched on it. Do you happen to have any thoughts on where where we're heading, if it's going to like a singularity from a protocol standpoint in the future, or we're going to basically have a continued use of CAN, Ethernet, LIN, even FlexRay to an extent?
Yeah, I mean, when you look at it, and I mentioned about the vision of this all Ethernet in-vehicle network, and one of the reasons for that is because the car is a device. It's like an ultimate mobile device, because it needs to be connected to the cloud. For connectivity, for autonomous driving, you need to be connected to the cloud. And really for that, you need an IP network. Just like IoT, we talk all about that. It's not too far dissimilar to that. So from protocols, a lot of it is IP based, and if you look at any IP network, Ethernet is the physical layer. Ethernet is not a protocol in itself, it's really a physical layer to put those protocols on, and it's application specific, so you can use any protocol. So from a general system point of view, yes, there are other protocols in there. We all know about TCP/IP and things like that. But that's another advantage of Ethernet is the fact that the software, the knowledge is all there. Things or to security. So it's not like we're inventing anything here. We're using well-known technology, protocols, hardware and software to solve these solutions.
Okay. Dovetailing in with that, are we likely to soon see multi-gigabit Ethernet in cars in production?
Okay. I guess yes. I mean, today, when we look at speeds of Ethernet, we've had 100 meg, 100 base T1, which is one pair, very light, low-cost cable, for a number of years now. And probably in the last 2 or 3 years, gigabit, 1000 meg, if you like, gigabit is pretty common. For automotive, the IEEE Ethernet standards are moving up as well as down. For multi-gig, I think in 2020 there was 802.3CH, which was 2.5, 5, and 10 gig. And that's really, from about 2025, and Dave touched on this, when you start using level 3 autonomous features, bandwidth goes up, and that's really, I think, 2025 is what you'll see in production vehicles starting to use multi-gig. First of all 2.5, then it soon goes to 5, then 10. As you move up those levels between 2025 and 2030, I would pretty much expect multi-gigabit Ethernet in vehicles to be relatively common.
Nice.
Awesome. So there were a few commenters with fairly specific questions, and I have kind of recommended that they go in to the Design Week event portal and request a meeting with experts on eMobility and ADAS. So Suresh, that's that one's for you. So Clifford, if you don't mind, we haven't quite discussed this already.
Yeah.
If you don't mind, let's kind of give people an overview of when they can. I think there was a demo showcase where we can kind of have time for people to talk with the experts.
Right, so if you look at my screen, and I think you guys can, we have the entire portal up. You can request a specific meeting with any of the topics that we're talking to, but to Wayne's point, if you're specifically looking for eMobility, it's just as simple as a few clicks. You can request a personal demo, but also during this 10 a.m. to 12 p.m., so in 14 minutes once we get off the air, you guys will be able to actually chat live with some of these guys and some of their other colleagues. So it's a huge feature that took a lot of effort to get everybody on board with, but it's kind of phenomenal that you guys can request and just talk to Microchip experts.
Yeah, awesome. So I think we'll close out the questions there. If I didn't get to your question, please feel free to email it to livestream@microchip.com, and we'll have Clifford personally triage.
It alternates between Wayne and I every day, but yes. Well, cool. So I'll send us home. Thank you guys very much. Huge thank you to everybody in front of the camera, behind the camera. It takes like a small army to actually pull this off, and so it's really quite impressive that we did. Tomorrow, we won't be on at 9 a.m. Pacific time. There will be a coffee break, though, which is low-cost graphics and touch-based solutions, I believe, and you guys should definitely check that out. Design Week will be back at 11 Pacific Daylight Time, so make sure you tune in for that, and the topic will be network infrastructure. But once again, thank you to everybody, and most of all, thank you to the viewers, because without you, this wouldn't be happening. So stay happy, stay healthy, and I'll talk to you tomorrow. Bye.
Thanks, everyone.
Thanks a lot. Bye.